Hello, ladies and gentlemen, and welcome to 4, which is entitled The Graphical Method for Finding Images of Convex Mirrors. I've got a couple of examples. We're going to learn a couple of new equations right here, and we're going to apply them to a couple of physics problems, yes. And it goes to kind of supplement the what's the word I'm looking for? The ray tracings that we did in the last section. So there's 2 examples, and with the ray tracing. So here's our first example. One of my examples, it deals with a convex mirror, and one of them deals with a concave mirror. The 2 equations that we're going to be utilizing today are the mirror equation, which is 1 over f, and f stands for the focal length, and you have to be really careful because the focal length, if it's concave, it's negative, and if it's convex, that means it's positive. The distance to your image, this is what it's going to be asking a lot of times to find. The distance to your image, if it's a virtual image, that distance is negative, and if it's a real image, that distance is positive. The distance to your object is always going to be positive. Always positive. The magnification equation, this magnification, M stands for magnification. This weird equal sign is just saying it's magnification is that. It's a math word for the word is. HI is the height of your image. HO is the height of your object. Negative DI is the distance to your image. And DO, hi-ho, di-do. It's kind of like that Snow White song that you used to sing when you were very young. So let's give this its first application. It says that an image in a security mirror, a convex security mirror, has a negative 0.5 focal length and a 2-meter tall forklift is 5 meters from the mirror. What are the image position and image height? So what do we got here? We have the focal length. The focal length is negative 0.50 meters. We've got 2-meter tall. That's the height of my object. Is 2.0 meters. It's 5 meters. That's the distance to my object. It is 5.0 meters. It says, what are the image position? So what's the distance to the image? And what's the image height? What's the height of my image? So it's just a very simple application of this mirror equation. 1 over f is equal to 1 over do plus 1 over di. The focal length is negative 0.5. The distance to my object is 5. And the distance to my image is unknown. So we're going to solve this equation. Now this one's kind of tricky to solve if you don't know what you're doing with fractions. So I just ended up using my calculator to do it all. So I take 1 divided by negative 0.5. And I'm going to subtract 1 over 5, subtract 1/5, and that equals negative 2.2. Now you got to be careful. 1 over di equals negative 2.2. So di is going to equal 1 over that answer. So you take 1 divided by that, and you end up with negative 0.45 repeating. So that's the distance to my image, negative 0.45 meters. What this is also saying, since it's the distance to your image is negative, is that it's virtual. It's not a real image. To find the height, you're going to use that other equation, hi over ho equals negative di over do. We'll just plug in everything we need. We don't know the height of our image. The height of our object is 2 meters. The distance to our image is negative 0.45. So see how the negative and the negatives cancel out. And the distance to my object is 5. So this is just going to be a cross multiplication and solve. So I'm going to take 0.45, 4545 repeating, times 2. And then I'm going to divide by 5. And I end up with negative 0.18 actually, it should be a positive number because I forgot to get rid of my negative there. So the height of my image is 0.18. Which means it's smaller. The height of my image, 0.18 meters. So that means that our height is smaller than, but it also means that it's upright. So because this is positive, it's upright. So here are the two pieces that we needed to know. Now, what I've done for you is I kind of made a scale image of this. These equations right here actually take the place of drawing those ray tracings that we did. And I just wanted to show you how this works. So here's what I've got. I've got the 2 meter tall forklift, and I think that if I look at this is 2 meters. See how it's from 5 to 7, and it should be 5 meters from our mirror. So I put this over here just to double check. Look at it, it's 5 meters. I should be able to do, if I do a really good job with my ray tracings, I should be able to find the exact same answer that I found here. So this guy, and I got to figure out what my focal length, remember the focal length of this thing was -1/2. So here's the focal length. Wow, that's really tiny. So then my reflected ray is going to look like this off this guy. And then the second ray is going to go to the middle, and then it's going to reflect off at the same height. So I go back to this guy, reflects off. Now, if I do a good job of making all straight lines, where this ray meets right here, and this ray meets right here, which I'll do in straight lines very nicely in a second, it should equal the numbers that I just had. So let's make some dotted lines to the focus. So here, here's where my object is, my image is located. If you look at it, it's 0.45. I mean, it's not quite. You see the image is a little bit shy of the 0.5, so I would say that the distance to my image, this distance from here to here, the distance to my image, it's a negative because it's virtual, and it's almost a half, so I'd say it's right around this, and which matches up pretty nicely to my distance. And then my height, I measure this thing, measure the height of it, turn my ruler. Boy, it looks like about 0.2. So the height of it, the height of my image, which matches up very nicely. So this, if you do a nice ray tracing or you do the math, they should give you the same answer. And then lastly, I want to do a concave mirror problem. A concave mirror has a radius of curvature of 20 centimeters. An object 2 centimeters high is placed 30 centimeters from this mirror. Where is the image located? How tall is the image? And is the image real or virtual? So let's see what we've got here. I could draw a rough sketch here. It's concave. The radius of curvature is 20 centimeters. So that means that the focus is half of that, which is 10. An object is 2 centimeters high, is placed 30 centimeters. So your object is way out here. So just to kind of give you an idea of what we're looking at, ray 1 comes in and it bounces through the focus. Ray 2 is going to come in and bounce back. So here's my image. I bet my image is going to be, I bet the height of the image is going to be negative because it's upside down. I bet it's going to be smaller than, so I'm going to guess it's probably around 1.5 centimeters. That's my guess. The distance to my image, this is going to be a positive number because it's a real image. And my guess is it's going to be between the center and the focus. So I'm looking for it to be around 15 centimeters. So we'll just see. We'll go through the actual math here to figure out where it's going to be. So 1 over the focal length equals 1 over di over 1 over do. So my focal length is 10 centimeters. The distance to my image is unknown, and the distance to my object is 30. So I'm going to take 1/10, which is basically 3/30. 3/30 minus 1/30 is 2/30, which is 1/15. So then di equals 15. So I didn't even have to pull my calculator out. And you'll note it had matched my prediction pretty darn good. I thought it was going to be around 15, and I also thought it was going to be positive, and I was right. The next part, figuring out how tall it is. I'm going to go hi-ho, di-do. Height of my image is 2 centimeters tall. Height of my object, I take that back. I don't know the height of my image. The height of my object is 2. Distance to my image is 15. Distance to my object is 30. Okay. Well, this is basically 1/2. 15 over 30 is 1/2. So this is going to be -1 because that will make it equal. -1. So my height of my image is -1.0 centimeters. And I can confirm that that's kind of what I was thinking about when I actually made it. So these equations are pretty simple. I mean, they deal with fractions, which is what makes them difficult. But here's the real challenge: is knowing that when the focal point, when it's a convex, put in a negative number for the focus. I'm sorry, when it's concave, put in a negative number for the focus. When it's convex, that's when it's positive. The distance to your image, if it's virtual, that's negative. If it's real, it's positive. That's why on that sheet that you got in the day prior, that I focused on, if it's a virtual image, then you should get a negative number. If it's a real image, you should get a positive number for your distance to your image. If the focal length, if it's convex, then it's going to be negative. If it's concave, then it's going to be positive. So what we're doing in the ray tracing realm translates right directly into the lens, mirror, and magnification equation because of those positives and negatives.